All right, so welcome back. We're going to first start, you remember we had this sort of simple 2x2 where we had qualitative to quantitative types of validation and first principles to experimental. And we're going to start out right here in first principles quantitative. We're going to talk mostly about sort of the idea of using the principles of conservation to ask the question, does my model actually make sense? And there are a number of points to sort of make on this. The first is don't use momentum conservation.
Why not?
Well, actually, you should use momentum conservation to come up with your model, right? When you write down F equals ma, you're using momentum conservation. But because you've used momentum conservation to create your model, you probably don't want to use momentum conservation to validate your model. So this is don't use momentum conservation to validate if you started with F equals ma. And to a certain extent, maybe that's not entirely true, because if you start out with F equals ma, you run a bunch of sort of algebra and calculus, and you manipulate the heck out of things, you get some equations, and then you check that those equations conserve momentum, you would be finding out that yes, the equations do the things that I said they would do at the outset. If you found out they didn't conserve momentum, you would say, wow, I think I did something stupid. Okay. So maybe it's too strong to say don't use momentum conservation, but momentum conservation is something you've already used.
So we're assuming that's been done.
Right. On the other hand, it is often really useful to use energy conservation. And I'm writing energy NRG because that's faster to write.
Got it.
And to use energy conservation, I think there are a few questions that we need to answer, right? So you have suggestions for those questions, Jason?
Well, first of all, is energy conserved? So
does that mean it's not conserved sometimes?
Well, sure. We can think about some of the systems we've looked at. I remember you talking about in the skateboard example that ramp hits the ground. You could lose energy when that collision happens.
Right. So keep in mind, when we talk about conserved here, of course, in the universe at large, energy is conserved. But the question that we're asking with is it conserved is the energy that we put into the system staying in the system as mechanical energy, right? So for example, when you have friction, that energy is still in the system, but it's heated something up. It's not actually energy that we're keeping track of anymore. In some sense, we'd say it's left the system because it's heated up.
So we have to be clear about the boundaries of our system when we think about conservation.
So here we're going to think really hard about the boundaries. And we're also going to think about the kinds of interactions that are involved.
Okay. So even if we establish that it's conserved, we want to know where in the system it is. So if we're talking about the hopper, do we have energy in the potential locations of the two parts of the hopper, kinetic energy, the rod and the ring?
And then once we ask where it's stored, then we can check whether the total amount is changing or not.
We just add them up?
Yep.
Wow.
Because energy is a scalar quantity, which is part of why it's useful to work with. Right, so those are the three questions we're going to ask. First, we're going to look at the system and understand it. Is it conserved? Secondly, if we think it is conserved, we're going to ask where is it stored, and then we're going to check and see if it's actually obeys the conservation law that we think it should.
Great.
Okay, so let's talk about this first, is it conserved question a bit. And to answer that question, we really have to think about the model that we've built and ask the question, what kinds of interactions are there in the model, right? So in the model, you can have two kinds of interactions. One type of interaction is what's called a conservative interaction.
So could you give an example of that?
So a conservative interaction is one where the energy is stored in such a way that it can be converted back to mechanical energy easily, okay? So, for example, a spring is an example of something that's conservative, right? You can take a spring, and if I do work on that spring, I stretch that spring out, right? And then if I let the spring go, the spring's going to actually give me that energy back, right? So I'm actually transferring energy between, I'm putting in energy as potential energy in the spring. It could then move this mass as kinetic energy, so I could have energy going back between potential energy and kinetic energy, but they'd both be mechanical forms of energy.
So if I got a frictionless ramp, I push a ball up a ramp, I'm doing some work on it, I have potential energy that's stored. I let it go. It drops down.
Right.
It gets converted to.
So, and,
kinetic again.
particularly if I think about the ramp, right? If I start, say, with the block having some initial velocity moving up the ramp, at this point it has a fair amount of kinetic energy. A little while later, it's gotten up to the top of the ramp. It's slowed down and stopped, but because it's higher, it's got some potential energy at this point. And if it turned around and slid back down the ramp, at this point, it would be going in the opposite direction. That kinetic and potential energy has gotten turned back to kinetic energy. If this were conservative, the amount of energy here would be the same as the amount of energy here. I wouldn't be losing any at all. Now, the other sort of option is that you can have non-conservative forces. And these are basically interactions that transfer mechanical energy into sort of other forms of energy, particularly heat is sort of the most common one. So for example, friction is an example of a non-conservative force, right? If I had friction in this case, right, when I started the block up the ramp, it would have some initial velocity. It would get to be a little bit less high because it would lose some energy to heating up the ramp on the way up. And then on the way back down, it would have a smaller velocity because some of the energy that I put in as mechanical energy initially would have been transferred to heat energy that was stored in the ramp that I'm not sort of keeping track of as part of my system. Okay, so friction's a good example of that. Drag is a good example of a non-conservative force.
Pool balls crashing into each other.
So actually, pool balls crashing into each other. So certainly, anytime you transfer energy into sound, you're going to lose some energy in that process. So. Although often with pool balls crashing into each other, you'd often assume that most of the energy is actually conserved in that collision. So that's sort of the first assessment that you need to make is the energy conserved? Right? I think we'll stop there, and in the next video we'll talk about calculating where the energy is.